These recordings are for the unit on temperature, heat, and thermodynamics. And this one is from chapter 15, number 5. What will be the final temperature of 100 grams of water? So 100 grams, that's only the amount here in the water glass, of 20 degrees Celsius, which is exactly 68 Fahrenheit, water when 100 grams of 40 degrees Celsius iron nails are submerged. So I'm just going to choose another color here. There we go. So 100 grams of iron nails, and they have a temperature of 40 degrees Celsius, submerged in it. So what's going to happen is that heat will flow from, and by the way, 40 degrees Celsius is 104 Fahrenheit. So we have 104 Fahrenheit nails here and 68 Fahrenheit water here, 40 Celsius, 20 Celsius. So heat will flow from the nails into the water. So heat will flow out of the nails, we call it Q, and heat will flow into the water, we call it Q in. Those two numbers are going to be the same. I'm going to use black again. So Q in into the water equals the heat out of the nails. Water. That was supposed to be an N, not males, but nails. There we go. Okay, the formula is given, and that one is C M delta T for the water, and on the other side it's, sorry, I'm writing somewhat up. Let's see, maybe this works a little bit better here, and then C M delta T for the nails. Okay, some numbers are given, such as the specific heat of iron is 0.12 calories per gram, 0.12 calories per gram and Celsius degrees. The mass of the iron is given as 100 grams, and then the temperature difference is going to be the initial temperature of the water, 40 degrees Celsius, minus the final temperature when the heat has flown out of the nails into the water. Okay, then for the water, it looks as follows. The specific heat capacity for water is the highest of all anyway, and it's defined as 1.0 calories per gram and Celsius degree. The mass of the water, they chose it in such a way that the mass is the same, so 100 grams, times then 20 degrees Celsius. And now I didn't leave enough space, so I'll try to pull that over here. There we go. Minus, oops, I actually did that slightly wrong here. Let me see if I can fix that. Because I wanted to write the final temperature first, minus 20 degrees Celsius, and the reason is that the water will heat up. So with the final temperature larger than 20 degrees, I have a positive here, and over here the nails are going to cool down, so with the 40 minus the final temperature, I also have a positive over here. Okay, this one looks quite complicated. In fact, it is relatively complicated. There is a quick way and there is a long way. The long way here is first, and this is where I would solve algebraically for the final temperature, and it's going to look as follows. going to try to make a nice fraction bar for a change. There we go. And I'm going to have the heat capacity of the water 1.0 times the temperature of the water, which is 20 degrees Celsius. And notice I leave out the units here so it doesn't get too long. Plus the heat capacity of the metal, which is 0.12 times the heat capacity, the temperature of the nails. That's what I meant, yeah, metals, nails. 40 degrees Celsius. Divide by the two heat capacities, 1.0 plus 0.12. And if you did the algebra, then you would figure out that indeed is what it is. As I said, I left out the units, so that means that the degrees Celsius here will survive for the final temperature. Notice that the 100 grams actually divided out. There we go. That's why they chose the same mass for the two. Okay, then when you multiply that out, you're going to come up with the following. I'm going to do this on the calculator. Okay, so let's see, parentheses 1 times 20 plus 0.12 times 40, parentheses, divide by the two added together, so 1.0 plus 0.12, parentheses, and I come up with 22.1 degrees Celsius as the final temperature. As you see, there was quite some algebra involved here in order to arrive at that end result. If we look at it and we say, well, does that result make sense? Well, we have the nails at 4 degrees Celsius and the water at 20 degrees Celsius. The water has a much higher heat capacity. That means it needs a whole lot more heat in order to heat up. That heat is not supplied because the nails have such a low heat capacity of 0.12. So that means that the final temperature should be relatively close to that of the water, and that's indeed what it is, relatively close, 22 degrees Celsius, which is in the neighborhood of 72 Fahrenheit. Okay, I said there is a quick way, and this quick way is an approximation, and it only works if the masses are the same. So here's the quick way. We compare the heat capacities of 1.0 and 0.12 and see what kind of ratio that is. So I divide the two, and when you do 1.0 divided by 0.12, you come up with roughly 8. If you do it a little bit more exact, you come up actually with 8.3 repeating. And now take the temperature difference, so between the two, that is, so 40 minus 20 degrees Celsius, and that should be written as actually Celsius degrees because it's a temperature difference. So Celsius degrees, and divide that by that ratio that I just computed, and you will see that you come up with 2.4 Celsius degrees, and I add that to the original temperature of the water, and I come up with 22.4 degrees Celsius. And as I said, it's only an approximation, and it's a quick way only because the masses are the same and I don't need to include those. So if you rather want to do it this quick way here, compare the heat capacities, divide that factor into the temperature difference between the two, and you come up relatively quickly with how much the water is heating up, by how much the water is heating up. chapter 15, number 7. Suppose that the 1.3 kilometer main span of steel for the Golden Gate Bridge, so the length is 1,300 meters, back to the standard unit for length, Golden Gate Bridge, and it's made out of steel. You'll get to it in just a moment. Had no expansion joints. Actually it does, but hypothetically has no expansion joints. How much longer would it be for an increase in temperature of 15 Celsius degrees? So what happens if the temperature was increased by 15 Celsius degrees, or 24 degrees Celsius, for example, from just freezing 32 Fahrenheit to 56 Fahrenheit, and that would be the same as going from 0 to 15 degrees Celsius. Okay, there is a equation is given here is that the increase in change, the increase in length, equals the length, the original length, times the coefficient of linear expansion alpha times the temperature difference. That's why steel was important, because each material has its own coefficient of linear expansion, and steel is given as alpha equals 11 times 10 to the negative 6 1 over Celsius degrees. Notice that this is not quite scientific notation, but tables listed that way so that most materials can be given as 10 to the negative 6. Okay, so the increase in length is going to be 1,300 meters times 11 times 10 to the negative 6, 1 over Celsius degrees, times 15 Celsius degrees. Made a slight mistake here earlier. This should be written as Celsius degrees. All temperatures differences are written as Celsius degrees. I don't think our book pays attention to that, but that's the case. And then that comes out to, well, we'll see in a moment. First of all, these units here divide each other, and we will come up with simply meters. And we go to the graphing calculator and see how much that is. So that was 1,300 times 11, and then 10 to the negative 6, that's how my calculator is doing it, times 15, and I come up with 0.21 meters. So looks like two significant figures as well. 0.21 meters, a little bit less than a foot, or approximately 8 inches. That's small compared to 1,300 meters, which is almost a mile, but 8 inches is not negligible. That's why the bridge actually does have expansion joints. Problem 8 says a 10-meter long steel wire, so 10 meter long, actually 10.00 meter long steel wire supports a pendulum bob at its end. How many millimeters longer is the wire when the temperature increases by 20 Celsius degrees? So delta T equals 20.0 Celsius degrees. Again, for the steel, that's alpha equals 11 times 10 to the negative 6, 1 over Celsius degrees. And then the increase in length is 10.00 meters times 11 times 10 to the negative 6, 1 over Celsius degrees, times 20.0 Celsius degrees. Again, the Celsius degrees divide, and on the calculator it's going to be 10 times 11 10 to the negative 6 times 20 Celsius degrees 0.0022 meters. 0.0022 meters, and that would be then 2.2 millimeters. And I believe we have 3 significant figures actually. Nope, 2, because of the steel giving only as 2 significant figures right here. So 2.2 millimeters, roughly a tenth of an inch. Number 9 says 2 equal length strips of aluminum and steel are heated. Which expands more? How much more? That is, by what factor is one expansion greater than the other? So here in my drawing, perhaps the upper one should be steel and the lower part should be aluminum. And look at that way, that if I heat up this bimetallic strip and it's supposed to move up, then it's the aluminum at the bottom that has to expand more and the steel less in order to make it curve upwards. Okay, notice that there are actually no more numbers given. The only ones that really are given are the coefficients of linear expansion. We already had this one in the past couple of problems. And then for the steel, it's also given in the book as 24 times 10 to the negative 6 or Celsius degrees. And really it says what is the ratio, or what is the factor by how much one expands more than the other. Well, it's simply the ratio of the two coefficients of linear expansion, so 24 over 11, that comes out to a rounded 2.2. So 2.2 times more is what the aluminum is expanding than the steel. As I said, there are no numbers given on this problem, but if you took numbers and you plugged them in, for example, from the last problem where you said, okay, let's assume that we have a length of 10 meters, and so 10 meters and a temperature difference of 20 Celsius degrees, well, then for the steel we would come up with 2.2 millimeters. We already know that because we calculated it in the last problem. And for the aluminum, we would have virtually the same calculation, except right here we would have to plug in 24, and that would give us 4.8 millimeters. So delta L for the aluminum comes out to, what was it again, 4.8? Yeah, 4.8 millimeters. And there you see that ratio is that 2.2 between the two. This is a re-recording of this problem from chapter 16 on the food value, respectively how much heat a burning peanut gives off in order to heat water. It's a re-recording. As you can see, I already worked out the algebra. However, I did make a mistake, and so some numbers that you see here, actually most of them are correct, but my end result is not, and I will erase that once I get there. Okay. Anyway, the problem reads as follows. In lab, Will burns a 0.6 gram peanut beneath 50 grams of water, which increases in temperature from 22 degrees Celsius to 50 degrees Celsius. The amount of heat absorbed by the water can be found with the equation Q equals Cm delta T, where Q is the amount of heat, C the specific heat of water, M the mass of water, and delta T the change in the water's temperature. A. Assuming that 40% of the heat released makes its way to the water, show that the food value of the peanut is 3,500 calories, or 3.5 food calories. That's for capital C. B. What is the food value in calories per gram in food calories, calories, and capital C again per gram. Okay. So, what I have here is 50 grams of water. There's a 0.6 gram peanut that is burning, putting heat into the water, and it says that the amount of heat it puts in is actually only 40% efficient, which means the other 60% are given off to the air, or are not reaching the water in other means. That's what's written here, 40% efficiency. These are temperatures of the water: 50 degrees Celsius when it's warm and 22 degrees Celsius when it starts, which means the temperature difference is 28 Celsius degrees. Here's the equation. Heat flow equals the specific heat capacity of water. There it is, 1.00 kilograms per grams in Celsius degrees. The mass of the water, 50 grams. Notice that the grams here and here divide out, and delta T is 28 degrees Celsius degrees, and again the Celsius degrees divides out, which is the calorie, which means that the calorie survives at the end. So it's 1.00 times 50 times 28, which is 1,400 calories. That so far is the correct result. That's how much heat the water receives. However, then I made a mistake in my first recording, and that is I multiplied with 40%. That is not true. I'll show you what I have to do. 1,400 calories is what the water receives, but that is only 40% of what the burning peanut gives off, which means what the burning peanuts give off must be quite a bit higher. How much higher? Well, what I have to do is not multiply with 40%, but divide by 0.4. Dividing by a percentage is rather strange, so I'm not going to do that, but instead I divide by 0.40. So there it is, divide by 0.40, and then I come up with, and I guess I could make a nicer looking fraction bar. Not fraction bar, but straight line here that gives me my result, and that means after dividing I come up with 3,500 calories. Again, that is the amount of heat that the peanut gives off, 3,500 calories, 40% of which is what the water receives, and 40% of that is the 1,400 calories that I calculated earlier. That one written in food calories are therefore 3.5 calories with a capital C. The second one says part B says what is the food value in calories per gram. So what I'm going to do here is I divide the number of calories, which is now the correct 3,500 calories, divided by 0.6 grams. So, and that comes out to around 5,800 calories per grams, or 5.8 food calories per grams. And now the problem is correct. Okay, number 3, which says pounding a nail into wood makes the nail warmer. Suppose that a hammer exerts an average force of 500 newtons on a 6 centimeter steel nail when it drives into a piece of wood. So we have a force of 500 newtons, that's about 100 pounds, on a 6 centimeter steel nail. So 6 centimeters steel nail, that's a couple of inches. When it drives into a piece of wood, the nail becomes hotter. I know that from trying to screw screws in, and if I don't pre-drill the hole, then wow, yeah, my screw does become pretty warm to the touch, pretty hot. And I noticed that when I try to turn a screwdriver, that it's so hard that I exert a lot of friction, and actually my hands ache and become warm as well. Anyway, if all the heat goes to the nail, calculate its increase in temperature. Assume that the specific heat capacity of steel is 450 joules. So here they're using a different unit. Instead of calories, they use joules. It's the SI unit, the standard unit, 450 joules per kilogram and Celsius degrees. Okay, let's see. The original question was calculate its increase in temperature. So they're asking for by how much does the temperature increase. Well, what I'm doing here is I exert a certain amount of work, and that will be transferred into heat. So I work the nail on there, and then when I'm done, then that energy is gone. Well, it's heat, of course. The work I can define as the force that I exert times the distance, and the heat I can define as the specific heat capacity times the mass times the change in temperature. The first one is going to be 500 newtons times 6 centimeters, so 0.06 meters. Standard units, we're going to come up with 30, and standard units, Newton meters, then will be joules. Nice, because I need that here as well. So here I'm going to have 30 joules, and that equals, because again the work becomes then the heat, and that equals 450 joules per kilogram and Celsius degree times the mass times the temperature difference. Oops, slight problem. We have two unknowns, mass and delta T. I believe in this problem what the author forgot is to supply a mass. So I looked them up, 2-inch nails or 2 1/4-inch nails, and I came up with a mass of 5 grams, or of course 0.005 kilograms. So the delta T here will then calculate as 30 joules, and trying to get a nicer looking fraction bar than what I usually do. 30 joules divided by 450 joules per kilogram Celsius degrees times 0.005 kilograms. These two divide, and I come up with delta T equals 13 Celsius degrees. Notice that divide by the inverse of Celsius degrees, and you're actually multiplying. So 13 Celsius degrees then means that if I started at room temperature of 20 degrees Celsius, I would heat up the nail to 33 degrees Celsius, so from around 70 Fahrenheit to approximately 90 Fahrenheit. Problem 4. A container of hot water at 80 Celsius degrees cools to 79 degrees Celsius in 15 seconds. So 80 degrees Celsius to 79 degrees Celsius in 15 seconds. When it is placed in a 20 degree Celsius room, so 20 degrees Celsius room. Use Newton's law of cooling to estimate the time it will take for the container to cool from 50 to 49, and still later to cool from 40 to 39 degrees Celsius. So 50 to 49, which is the same temperature difference, just 1 degree, and then later on from 40 to 39. The rate of cooling is given as proportional to the temperature difference between what is cooling, the 80 degrees Celsius water, or that's around 180 Fahrenheit water, to the 20 degrees Celsius room, so the 70 Fahrenheit room. So those that's proportional. So initially what we have, I'm going to use a different color, is we have delta T of, I don't know why it's always doing that thick. I'll try to, there we go. It'll work a little better. We have 60 Celsius degrees initially. Later on we're going to have delta T equals 30 Celsius degrees. Notice 50 compared to the 20-degree room. And then still later on delta T equals 20 Celsius degrees, the 40-degree water compared to the 20-degree room. So here initially we have 60 Celsius degrees, and the rate of cooling, it takes 15 seconds. And then we're going to have 30 Celsius degrees, and then we have 20 Celsius degrees. The rate of cooling is how fast it cools in a certain amount of time. Since we actually have the time given, we would have to invert that number, but I believe you can also see that if it takes 15 seconds for a 60-degree difference to cool just by 1 degree, so 1 degree Celsius per 15 seconds, then over here you can see that it will take twice as long, or the rate of cooling has halved. So we're going to have 30 seconds, and then here we have 1 Celsius degree, where this one is 1/3 of the original one. That means it takes 3 times as long. And you may know that from other applications, a very hot cup of coffee or cup of soup will drop faster in temperature than a lukewarm soup. Of course, still you're going to eat the lukewarm soup, but because the temperature is closer to room temperature for the lukewarm soup, it takes longer to cool even further than a very hot soup, because that's what the rate of cooling says. Number 6, which says, at a certain location the solar power per unit area reaching the Earth's surface is 200 watts per square meter. So 200 watts per square meter. Averaged over a 24-hour day. Actually, the solar constant is defined as 1000 watt per square meter. That's how much energy we get from the sun for every square meter, or every 10 square feet. But it says here average over a 24-hour day, and that may include also some clouds. If you live in a house whose average power requirement is 3 kilowatts, so 3 kilowatt or 3000 watt is the average power requirement, and you can convert solar power to electric power with 10% efficiency, and I heard that from a contractor the other day. Could be as high as 18% efficiency. That means that the other 90% in this case here cannot be converted to electric power. How large a collector area will you need to meet all your household energy requirements from solar energy? Will it fit in your yard? Okay, so we have an amount of power of 3000 watts that is needed for the house, and that equals the area that is needed times the 200 watts per square meter times the 10% efficiency, so times 0.1. And when you calculate that out, well, on the right hand side here, or on the lower side, we're going to have 200 times 0.1 is 20. We divide that 20 into 3000, and we come up with an area of 150 square meters, or 1500 square feet. And probably your roof is not that large. Perhaps your yard is. Chapter 17, problem 4. If 50 grams of hot water at 80 degrees Celsius So 50 grams of hot water. Doesn't look hot, but oh well. 80 degrees Celsius is around 180, 175 Fahrenheit. Is poured into a cavity in a very large block of ice at 0 degrees Celsius. So the ice here, it says actually very large ice at 0 degrees Celsius. So ice, of course, could be colder, so the 0 degrees Celsius ice is at the verge of melting. What will be the final temperature of the water in the cavity? How much ice must melt in order to cool the hot water down to this temperature? Now, technically, we could say that if we had a limited amount of ice and we have 80 degrees Celsius water, 50 grams, and we pour it in there, well, the water, of course, is going to drop its temperature, and the ice is going to melt, for which it needs heat. That's the latent heat of fusion that it needs, and then it's going to increase its temperature. But it says it's a very large amount of ice, so that leads us to a conclusion that we say, okay, the ice is actually going to stay with the exception of a little small amount that will actually melt, and all the liquid hot water will become as cold as possible, and in fact it will go down to 0 degrees Celsius, and that is the answer to the first question, 0 degrees Celsius of liquid water. Well, here this one is 0 degrees Celsius of solid ice. The difference between the two is that we would still need heat, the latent heat, the hidden heat that cannot be measured by a thermometer, in order to get from 0 degrees Celsius solid to 0 degrees Celsius liquid, or to extract that same amount of heat in order to get the liquid down to the solid. Okay, second question says how much ice must melt in order to cool the hot water down to this temperature. Well, let's see actually how much heat is being actually extracted from the hot water, and that of course is that often used equation, specific heat capacity times mass times the change in temperature, and that is the 1.00 calories per gram and Celsius degree times the 50 grams. Again, I don't need to convert that to kilograms because the specific heat capacity is given per gram, times the drop in temperature, which is 80 Celsius degrees. I use it as such that I say, okay, I divide my lower temperature from my high temperature, I come up with a positive number. So the amount of heat that needs to be extracted from the hot water is going to be 4,000 calories, because the grams divide and the Celsius divide, leaving behind the calories. Now it says how much ice would have to melt in order to cool it down, because the ice cannot get any warmer than 0 degrees Celsius, so the only way it can supply the heat is absorb the heat is actually by melting, and that would be the latent heat of fusion, which is given as Q equals mass times capital L. Well, this one is 4,000 calories, and that's an equal times the mass equals mass times the latent heat of fusion is given as 80 calories per gram. And when you look at the numbers, we're going to come up with mass equals 50 grams of ice has to melt. That is the same amount of hot water. That's just a coincidence, and the reason that happened is because as the latent heat has a number 80, that the temperature chosen that it's dropping is also 80, and that's why we come up with the same mass. If they had chosen another original temperature of 90 or 60 degrees Celsius, then we would come up with a different amount of ice. Number 5, a 50-gram chunk of 80 degrees Celsius iron is dropped into a cavity in a very large block of ice. So we have 50-gram chunk, approximately 2 ounces. I guess I need a few more nails here. Well, that could be actually correct. 50 grams of 80 degrees Celsius nails, or iron actually. is dropped into a cavity in a very large block of ice at 0 degrees Celsius. How many grams of ice will melt? Pretty similar calculation as the last one, so I would have to say that the iron is going to drop down to 0 degrees Celsius. Of course, here's no question, the iron is solid anyway, so it's going to stay solid. But the specific heat capacity of iron is 0.11 calories per gram and Celsius degree times 50 grams times a temperature difference of 80 Celsius degrees, because it goes down to the 0 degrees Celsius to meet the ice. And again, it's a very large block of ice, so they assume the ice is still going to stay at 0 degrees Celsius without not even heating up a fraction of a degree. Okay, multiply those three numbers. The units here cancel or divide, and we come up with 440 calories. And then it says how many grams of ice will melt. Well, as I said, similar calculation as before, or virtually the same. Mass equals 440 calories divided by 80 calories per gram as the latent heat of fusion, and that comes out to 5.5 grams of ice. Why the big difference compared to the last one? Even though it seems like the numbers are the same, in the last one it was also 50 grams of water, but the big difference is that any kind of material other than water has a much lower heat capacity, as evidenced by the 0.11, which is approximately a ninth. That's why also just a ninth of the ice has to melt in order to get the pretty warm 170 Fahrenheit, 180 Fahrenheit iron down to 0. So a much smaller amount of ice has to melt to do that to the iron than compared to the hot water. Number 6, which says calculate the height that a block of ice at 0 degrees Celsius must be dropped to completely melt upon impact. Assume no air resistance and that all the energy goes into melting the ice. So as the block here drops, it starts out with some potential energy, which is then converted to kinetic energy, which is then converted to heat upon impact. And in fact, it says in the parentheses, hint, equate the joules of gravitational potential energy to the product of the mass of ice and its heat of fusion. In the previous problems, it was given as 80 calories per gram. Here's the SI unit of 335,000 joules per kilogram. So capital L, instead of 80 calories per gram, here it is 335,000 joules per kilogram. Actually, same number, just different units. That's why it looks different. Do you see why the answer doesn't depend on mass? Oh yeah, I guess they didn't give us the mass. Well, let's see what happens. Potential energy at the top is mass times gravity, acceleration due to gravity, times height. And the heat here is mass times latent heat of fusion, and the entire potential energy is being converted to the heat. So mass, gravity, height equals mass times latent heat of fusion, and so the mass divides out. That's why it doesn't matter if it's a kilogram or 80 pounds or 2 tons. So here we now have pretty much the height as L divided by G, or 335,000. Okay, maybe I shouldn't have squeezed it in that much kilograms. I'm gonna move this out of the way. So divide by, I guess I'll use a nicer looking fraction bar. Divide by 10 meters per second squared. And I still need to move this out of the way. So the height comes out to 33,500. Yeah, some kind of unit here. I would have to make a whole unit analysis. The joule is actually kilograms meter squared per second squared, and then we can see, okay, these divide out, the kilograms divide out, and then one of the meters divides out, and we're left behind with meters. So hypothetically, if we drop that chunk of ice from a height of 33.5 kilometers or 20 miles up, then it would melt upon impact. What it kind of shows here is that, besides that it's kind of ridiculous and totally hypothetical, is that the latent heat of fusion for ice is quite big. In order to provide that much energy, in this case potential energy, you have to lift to a very large height to provide that much energy just to melt it. Of course, we use different means to melt ice or to solidify liquid water. But it's a huge amount of energy because the latent heat of fusion and the latent heat of vaporization are very large, and the specific heat capacity for water is large. The latent heat of vaporization, we know that it's very large because it takes a long time to totally evaporate a pot full of liquid water. Chapter 17, number 7. It says a 10 kilogram iron ball is dropped onto a pavement from a height of 100 meters. So we have 10 kilograms of iron. If half of the heat generated goes into warming the ball, so 50% efficiency, that means probably the other 50% is used to warm the pavement. Find the temperature increase of the ball, and the specific heat capacity of iron is given as 450 joules per calorie and joules per kilograms and Celsius degrees. That's equivalent to the 0.11 calories per gram in Celsius degree. Why is the answer the same for a ball of any mass? Well, let's see what happens from a height of 100 meter. Oh, I guess I didn't write that down yet. So height of 100 meter. Okay, again we have a certain amount of potential energy, of which 50%, so 0.5, will be converted into heating the ball, so that equals Q. And then we have the potential energy given as mass times gravity times height, and here we have specific heat capacity times mass times temperature difference, and the mass divides out, so we actually don't need the 10 kilograms. That's why. That actually answers the second question. The temperature difference here is independent of the mass. Oh, I almost forgot that 50% efficiency, so there's a 0.5 in the front here. So 0.5 times 10 meters per second squared times a height of 100 meters, that's about 300 feet, equals 450 joules per kilogram and Celsius degree, and then times whatever temperature difference we're going to calculate. So delta T, that delta T over here equals everything over here divided by the 450, so delta T equals fraction bar 0.5 times, that's not a minus, that's a times 10 meters per second squared times 100 meters divided by 450. Ooh, and here comes the joules. Kilograms meter squared per second squared. divide that whole thing by kilograms and Celsius degrees. Okay, let's see, kilograms are dividing, the second squares are dividing, the meter squared right here, there's a meter here and there's a meter there that they're dividing with, and the only one left is divide by a fraction which has the Celsius degrees in the denominator, so that means that the Celsius degree will turn up on the top, and then we have 0.5 times 10 is 5, times 100 is 500, 500 divided by 450, you may do that on the calculator, comes out to around at 1.1 Celsius degrees. So it does increase a little bit in temperature. Chapter 18, number 1. During a certain thermodynamic process, a sample of gas expands and cools, reducing its internal energy by 3000 joules. While no heat is added or taken away, how much work is done during this process? So we assume that this one here expands, and that due to the expansion, the internal energy is going down by 3000 joules. So internal energy decreases, and that energy has to go somewhere. Well, there is no heat escaping or going in, so that's not where it's going, and the only other way where it can go is by the amount of work that energy is doing, and so that amount of work comes out to 3000 joules. And this is, by the way, not a perfect engine, it's simply just the adiabatic process of part of an engine where no heat is flowing in or out, and all the internal energy is used as work in this case. Number 2, which says, what is the ideal efficiency of an automobile engine which fuel is heated to 2700 kelvins and the outdoor air is at 270 kelvins? Okay, so we have 2700 kelvins. Notice that if this was given as 2400, this is rounded by the way, 2400 degrees Celsius, that we would have to convert that first to the absolute temperature in kelvins. Then we have an outdoor temperature of 270 kelvins, which is again roughly 0 degrees Celsius. And again, if we had given this as 0 degrees Celsius, we would have to convert it first to 270 kelvins. Okay, the efficiency is computed as T hot minus T cold there we go, divided by T hot. So we have 2700 kelvins minus 270 kelvins divided by 270 kelvins. And when you do that, you have 2430 kelvins divided by 270 kelvins, which is oops, I made a mistake, 2700 kelvins, it said hot, which is 0.9, respectively 90%. Looks a little bit high for an automobile engine. They usually come in at around 30 to 40, maybe tops 50%. Chapter 18, problem 3, which says calculate the Carnot efficiency of an OTEC power plant that operates on a temperature difference between deep 4 degrees Celsius water and 25 degrees Celsius surface water. So here we have 25 degrees Celsius on the surface, and here we have 4 degrees Celsius at the bottom. This makes sense because the most dense water will go to the bottom, and water is most dense at 4 degrees Celsius. First of all, it said OTEC. By the way, OTEC means ocean thermal energy conversion. So it's an energy method, energy producing method that takes advantage of the difference in temperature between the different levels of ocean water. And yeah, here you have a difference of 21 degrees Celsius, and that's enough to generate energy with however principle that is working. First of all, we have to convert these to the absolute temperatures. So this one is going to come in at 298 kelvins. Then this one is going to come in at 277 kelvins. And again, for the efficiency, we have T hot 298 minus 277 divided by the T hot 298 kelvins. And when you do that on a calculator, you're going to come up with 298 minus 277, where I knew that would be 21, divided by 298, and we come up with 7% efficiency. And now you can say, hey, that's not a lot, but however, that energy is readily available. Just build a plant that takes advantage of the temperature difference, and then it's virtually free energy because you don't need any fuel to put in it. You just take advantage of the ocean difference, and well, yeah, you only have a 7% efficiency, but hey, that's you have pretty much unlimited amount of water that you can draw from unlimited amount of water with the temperature difference and the heat that is stored between the two. And number 4, on a chilly day, on a chilly 10 degrees Celsius day, your friend who likes cold weather says she wishes it were twice as cold. Taking this literally, what temperature would this be? There's no drawing here. I guess I could drawing of a person, but 10 degrees Celsius and half. Let's see what it says. Your friend who likes cold weather says she wishes it were twice as cold. So twice as cold, we assume that, it's 5 degrees Celsius. But no, that's not the case. If we take this, we have to take it as the absolute temperature. So we're going to come up with this one is the same as 283 kelvins. Twice as cold would then mean around at 142 kelvins, which then comes out to minus, and I subtract 273 here, comes out to minus 131 degrees Celsius, which is probably in the neighborhood of minus 200 Fahrenheit. So I don't think that she wants to do that. Problem 7. A heat pump moves heat from a cooler to a warmer place and is the heart of a refrigerator or an air conditioner. It is used to heat houses. The minimum work input needed to move energy uphill from T cold to T hot is minimum work equals energy moved times T hot minus T cold divided by T cold. Calculate the minimum work needed to move 1 joule of energy from inside a room at T cold equals 295 kelvins to the outdoors at T hot equals 308 kelvins. So let's see, we have from inside a room of 295 kelvins. So we're actually in the summer here. 295 kelvins would be 22 degrees Celsius or 70 Fahrenheit to the outdoor of 308 kelvins, which is 35 Celsius, or nice balmy 105 Fahrenheit. So here in part A, let's see. So this would be our part A, where then we're going to come out that the amount of work needed in order to do so is the energy that is being moved, and they just say, take a token 1 joule. So 1 joule times the temperature difference, so 308 kelvins minus 295 kelvins, and divide that by the cold temperature, 295 kelvins. Notice that's a little bit different than the last ones where we divided by the hot temperature. Depends on the engine type. Engine types where you convert heat to mechanical work. In their formula, you have to divide by the hot temperature. For here, for a cooling process, so for an air conditioner or a heat pump working in reverse, we have to divide by the cool temperature. On the practice test and on the proctored exam, pay attention that here we use the heat pump in order to heat, and we're back to the hot temperature actually. So pay a little bit of attention here when you take the practice test or the proctored exam. So I'm going to have 308 minus 295 divided by 295, so it's 13 divided by 295, and that comes out to 0.044 when you do that on the calculator, and that comes out to joules because the kelvins cancel. Okay, and then it says from inside a lab freezer at 173 kelvins, so part B, 173 kelvins, to a room at 293 kelvins, so the room is kind of room temperature, 20 Celsius or 68 Fahrenheit, while the lab freezer is minus 100 Celsius, or in the neighborhood of minus, is it 150 or minus 200 Fahrenheit, somewhere around there. So pretty cold, and the amount of work comes out to 1 joule times the temperature difference, which I may write as 120 kelvins, I think you can see that, divided by the lower temperature of 173 kelvins, and that comes out to 0.69 joules. All these answers seem like we're getting a freebie because the amount of work that we have to put in order to move 1 joule here is quite a bit less. That's why these are actually not given as efficiencies, but they're called the coefficient of performance, and what it means here is we put only 0.044 joules in order to move 1 joule, and the coefficient of performance is about 20, so we can move 20 times as much energy with a certain amount of work. That's why it's not given as an efficiency, because it would look a ridiculously large number. It's just about moving an amount of heat. It's actually not converting energy. The work, by the way, that is being put in here is then also deposited as heat to the outside. That's why with a refrigerator you're actually a little bit heating the kitchen. Okay, part C says from a helium refrigerator whose inside temperature, so maybe it's this one up here, hopefully not, part C, 4 kelvins, that's minus 269 Celsius or roughly minus 450 Fahrenheit, to a room temperature of 300 kelvins, that's actually 27 degrees Celsius, or in a neighborhood of, I believe, 85 Fahrenheit, top of my head. And here the work comes out to 1 joule times temperature difference of 296 kelvins divided by the lower temperature of 4 kelvins, and that comes out to 74 joules. So in this case it's actually that a lot of work needs to be done in order just to move 1 joule of heat out of the helium that wants to heat up in order to keep it cool.